Welcome back to ECE 220 for those of you that are here. Late night last night, apparently, getting the homework finished. Homework 6 is now behind you, and that's actually the material from homework 4, 5, and 6 that will be on content-wise exam number 2, which is 8 days away. Exam number 2. Exam number 2 is next Thursday, a week from Thursday, on the 17th of October. That will include homeworks 4, 5, and 6. Prior to that, Group B, your Lab 1 report is due today, and your pre-lab for Lab 2 is due on Saturday. We still have circuits to build with op-amps, and today what we want to do is create a combination of the inverting and non-inverting and create a difference amplifier, and then we'll redraw it differently, and hopefully that will provide some insight into why we even are so worried about this difference amp, and we'll introduce a couple of new terms, common mode and differential mode, and those will be helpful in our understanding of what's going on or how we can apply this difference amplifier. Since redrawing one of the circuits helped out, let's redraw the non-inverting amplifier circuit. You might see it drawn a different way, a way that we haven't drawn it yet, and I don't want that to confuse you, and hopefully we will get to the point where we will have time to talk about the input resistance of an op-amp circuit, and you can do that determination for all the different circuits that we've looked at so far, but we'll do it for one particular input resistance op-amp circuit. Here's what we want to dive into today, the difference amplifier. And now you can see that we have signals or sources applied through resistors to both the inverting input pin and the non-inverting input pin of our op-amp circuit. We do have a feedback connection, and note how these have been maybe relabeled. Now instead of R sub S and R sub F, we have A, B, C, and D. We have R sub A, R sub B in the inverting piece of the circuit, and we have R sub C and R sub D in the non-inverting piece of that circuit. And if we stay in the linear operating region, we will be able to assume that this is now satisfying properties of linear systems, and that's going to help us or provide us with one strategy for analyzing this circuit. And so now what we want to do is try to analyze this circuit. What is the output voltage, V sub 0, in terms of these two different sources, V sub A and V sub B? To help with that analysis, I've provided us with a hint. It's a linear circuit. Is that a helpful hint, or is that not helpful in terms of how we might analyze this circuit? And I might remind us that we have two input sources, not just one, we have two. And now we have a linear circuit. What was the last homework problem, I think, on homework number 6? What was the topic or subject of that? Superposition. Can we apply superposition to this? We have two independent sources. Let's look at them individually and then add up the result from each of those contributions that are provided to us separately. So that's what we want to do. First, we've noticed, hopefully, that we do have negative feedback, and 2, now in our analysis, we will, or we can use, we don't have to, but this might help us more clearly understand the contributions from each of those sources. So we're going to use superposition to analyze that circuit. And that's the linear circuit that we mentioned. We're using that linearity property to allow us to use the superposition principle. If that's the case, let's now say that part A, we're now going to look at 2 different parts. Part A, let's keep source A active, which means let's deactivate source B. If we deactivate V sub B, what would the circuit now look like? I haven't changed anything in the inverting part of the circuit. This is now V sub A, R sub A, R sub B. Here is our output voltage, and to make sure that we are remembering that we're applying superposition, let's say that that's V sub O sub A. It's the contribution of the output voltage from source A. And now what do we do if we are deactivating the source V sub B? What does that now look like if we deactivate that source? It depends on the source. What is the source? Current or voltage? Voltage. How do we deactivate voltage sources? We short them out. What does that allow us now to draw relative to the non-inverting pin of this op-amp circuit? We now had, this was R sub C, and now we said we can short out the voltage source, but we still had R sub D to worry about, or to keep track of. If we now have this picture, maybe the first thing we want to do is, well, we're going to be probably writing KCL equations relative to the node, the inverting node, V sub N, and that, since we have negative feedback, is going to be the same potential as V sub P. V sub N and V sub P are equal because of negative feedback. What is V sub P? This is now V sub P. What can we say about that? Can we say anything about this current I sub P? I sub P is 0. Is there anything on the other side of that node to provide current flow? No, those resistors are now connected to our common reference, so there's no current flowing. I sub P is equal to 0, which now says that because there's nothing else to provide any source of current, we now can say that V sub P is in fact equal to 0. Even though there's resistors there, both sides of those resistors are at the same potential. There's no current flowing. We have 0 volts for V sub P. And R sub B is there, which is providing us with the negative feedback. And we now know that V sub p, or this is the assumption that we make, we assume we're operating in the linear rate region, so we can say that the two input pin voltages are at the same value. We have the same potential at the input pins. V sub p is equal to V sub n, and we just convinced ourselves that V sub p was 0. So now V sub n is equal to 0. Let's now write KCL at that node. Here's now V sub n. And we said that that's 0. Let's sum our currents out of that node. We have a current flowing through R sub A. That's where we are, 0 minus V sub A. We have a current flowing through R sub B, and we said let's sum the currents out of V sub n. That's 0 minus V sub 0 sub A. And then we have no current flowing into that inverting pin. Our I sub n is equal to 0. KCL at V sub n says then we have 0 minus V sub A over R sub A plus 0 minus V sub 0A over R sub B plus I sub little n, which is 0, and that's equal to 0. And we can now solve that for the output voltage with one source active, and this source that's active is the A source, V sub A. We can now multiply both sides by R sub B, or multiply through by R sub B, put V sub OA on the other side, and we end up with V sub O sub A is now minus R sub B over R sub A, V sub A, and that really shouldn't surprise you. That's now the standard formula for our inverting amplifier. Because we had a standard interconnection in our circuit relative to the inverting pin. And now we just re-derived this formula. We had some different labeling on the resistors. We now labeled our feedback resistor as R sub B. Our input resistor is R sub A in that particular branch, giving us then minus R sub B over R sub A times V sub A, giving us the first component of our total answer for the output voltage. B, part B now, let's go ahead and deactivate V sub A. And let's just redraw the circuit. Now we are keeping V sub B. Here was R sub C and R sub D. This output is going to be a result of keeping the B source active. And now how do we redraw our inverting component or part of this circuit if we've now deactivated V sub A? What do we do now? Do you see what we need to do? We just short out V sub A and leave everything else alone, right? Or now we can keep R sub A and R sub B, but now the left side of R sub A is going to be grounded. We now have we're keeping our negative feedback through R sub B. R sub A now is connected to our common because we're now deactivating V sub A. What was our strategy in the last half of this analysis? What did we do first? First, we looked and we did see that we have negative feedback. But we were interested in this voltage at the non-inverting pin because with negative feedback, we can now assume and then check at the end whether or not V sub P and V sub N are equal. What is V sub P? Does anything there look familiar? This should look like an exam 1 problem. What is V sub P? It's a voltage divider. You now have two resistors that are dividing the voltage from V sub B. Or we now know that V sub P through a voltage divider is now R sub D over R sub C plus R sub D times V sub B. We have negative feedback, which allows us then to go ahead and assume that V sub P is equal to V sub N. We now have a virtual short between our input pins of the op-amp. And we can now use that information maybe in a little bit. Let's go ahead and just write KCL at V sub N and keep V sub N in there for now, just so we are clear where we're coming up with these expressions. Here's now V sub N. We have three currents leaving that node. One current is going into the inverting pin of the op-amp, and we know its input resistance is huge, so that's 0. That's little I sub n. The current going to the left through R sub A is V sub n minus 0 over R sub A. The current going to the right through R sub B V sub n minus V sub OB divided by R sub B plus this current that's 0 right here. And all of those sum to 0. If we start collecting terms, we now have 1 over R sub A and 1 over R sub B that are going to weight V sub n. And let's put V sub OB on the other side, and now let's multiply both sides by R sub B and realize that R sub B over R sub B is 1. We now have 1 plus R sub B over R sub A, and interchanging those terms, V sub n is equal to V sub OB. And we know that V sub n is in fact V sub P, and we have V sub P related to V sub B from our very first voltage divider. Putting all of those pieces together, we now can say that the contribution to the output voltage from source B is now 1 plus R sub B over R sub A times V sub n, but V sub n was V sub P, and V sub P was R sub D, this voltage divider relationship, between V sub B. We're using superposition to find the total output, V sub O. That now says that that is going to be due to the two pieces that we just found, minus R sub B over R sub A, V sub A, plus 1 plus R sub B over R sub A, R sub D over R sub C plus R sub D, V sub B. That's now our expression for the output voltage, V sub O, in this difference amplifier circuit is a weighted or scaled, a weighted difference of V sub A and V sub B. V sub B comes in with a positive coefficient. V sub A comes in with a negatively weighted coefficient. So we have a difference going on. Now you might say, well, that looks a little bit messy. Do we have to memorize that? Do we have to memorize all these formulas for the exam? You could rederive that, I hope. But does this expression simplify for specific resistor values? And I probably wouldn't have asked that question if I didn't have an affirmative answer. It does. Usually, we have a relationship between these R sub B's and R sub A's, the ratio. R sub B over R sub A is typically made to be the same as R sub D over R sub C. And if we even make it a little bit more equal, we can simply say, well, let's just let the numerators be the same and the denominators be the same, and that will definitely make the ratios the same. If we let R sub B equal R sub D and R sub A equal R sub C, then we can clean this relationship up. V sub O is now minus R sub B over R sub A, V sub A, plus 1 plus R sub B over R sub A. We haven't done anything yet, but now let's, in the denominator of that second term, let's go ahead and factor out R sub C. And we now have R sub B over R sub A the same as R sub D over R sub C. If we now add 1 to each of those, it's going to give us the same expression. That term cancels that term. And I hope you can see that this ratio that's remaining with R sub D equal to R sub B and R sub C equal to R sub A is the same as the weighting coefficient on V sub A. Or we can now rewrite this as V sub O, the output, under these conditions with the relationships, these equalities with our external resistors around this op-amp, now gives us R sub B over R sub A times the difference V sub B minus V sub A. And that's now our difference amplifier. Obviously, this depends very much on being able to equate all of these resistors, and we know that there's going to be tolerances, and that may not be true. So there are more elaborate ways of creating difference amplifiers. This just kind of gives you a feel for that process. Question? The question was, are we going to have to rederive all of these formulas, or should we just memorize the relationships based on the way the circuit is interconnected? Was that a paraphrased version of your question? I would say the answer is sort of a little of both. You probably want to just know what the inverting amplifier formula is. That's minus R sub F over R sub S times the input. Probably know the non-inverting formula, 1 plus R sub F over R sub S times, or whatever the values were, the resistor labels were. This one, if you say, oh, if we let all of these different combinations be the same, then this would be our difference equation. But you should be able to step through a lot of these sequences in order to get to where we were going, because some of the questions might be asking you a question halfway through the derivation. They may ask you to find V sub P, or they may ask you to find some other, like last time we had to find V8. And that wasn't in these formulas directly. So you need to understand the thought process in deriving these expressions. Maybe don't memorize all of them, but the ideas and the concepts you should start feeling more comfortable with or confident with. Hope that helped answer your question. So I'm basically saying a little of both. Know some of the formulas, the first two, inverting and non-inverting, and understand how to derive the others, because you may be asked to determine something partway through an analysis step, or find a current or a voltage somewhere in the amplifier circuit, and you're going, well, that's not in the formula, but you can work your way through there. Do you have negative feedback? What's V sub P? Let me write KCL at V sub N. You know how to do those steps. Let's now redraw this. I know you're very excited about drawing, or you wouldn't be in engineering, right? No. But you might see these circuits sketched or stretched and distorted and reshaped in different ways. Now what I want to do is try to help you understand that we can draw this difference amp to look more like what's on the right. The right maybe looks more symmetrical. Now we have a couple of resistors on top, a couple of resistors down below, but they are interconnected a little differently. R sub B goes to the positive side of the output voltage. R sub D goes to the common reference. Now what we want to do is try to connect both of these sources to our common node, and still have the same behavior on the left as we have on the right. How would we now do that? Can I now simply say, oh, if I didn't have to worry about the B, do you see how I could now put that top voltage source to look like V sub A, how I would label it? Doesn't it now just look like plus and minus V sub A? To be consistent with what you see on the left, And now let's do the same thought experiment on the bottom voltage source. We now want to connect this end to the reference node. And now how do we label the polarities if we want the bottom source to in fact be V sub B? Do we do plus minus, minus plus? We want it to look just like or behave exactly like the circuit on the left. Now we have two voltage sources connected to a common node, and that looks a little different, but in fact that's what was going on over here on the left. So do you see, if we just connect those commons together on the left, we end up with their negatives being the same? So there's V sub B. And if we wanted to, we could say, well, what is the KVL if I went around this path? What do I find? What kind of a relationship do I see happening between essentially this point here and that point there, because that's that point and that point, with the bottom node labeled as the positive polarity on delta V. This is now what I'm saying with the yellow highlight is, what's KVL around the yellow highlight? That got some music going. Did it stir up some music in you? What's KVL here? Well, we're starting at common, and then we're going immediately through the voltage source V sub A, entering the negative terminal first. So we now say minus V sub A. And now we're going across this air gap that we've labeled minus delta V, since we're entering its negative terminal next in this progression or walk around our KVL. Then we go into plus V sub B, and then we end up back where we started. Or if we simply put delta V on the other side, delta V now becomes V sub B minus V sub A. And that sort of then emphasizes the fact that we have a difference amplifier in play by redrawing that particular circuit. Well, if that's the case, why are we going through these redrawing gymnastics? To get in shape. Isn't that why we... All right, so there was the original, there's the redrawn, and now we can maybe more effectively see, oh, this delta V happening. Now you're probably questioning, why are we even so worried about this difference amplifier? Why is it so useful? And now what I want to do is have you think about what would happen in the lab. You're going to have noise. In real world, you're going to have noise floating around. What happens now if we have noise or interference coming in, let's say, to the traditional inverting amplifier circuit, where this V sub NO is an abbreviation for noise and interference, but it's kind of representative of as what we want. We don't want that. No, we would prefer that voltage. No, we wouldn't want it, but it's there. V noise. So we're adding that in to V sub S. What's the output going to be? I've already given you the formula. I now just needed you to tell me, what are you scaling through that resistor combination? If the noise wasn't there, if it was deactivated, then we would have the normal. But if we then applied superposition, we could say, oh, that's really all there is to it. But what's happening now in this unmodified version of the inverting amplifier circuit? What's happening now? If we have noise present, the noise is actually amplified. So what we want to do is, if we have a couple of signals, and if those two signals are really experiencing the same noise, maybe if we compared those two, we could get the signal information out by the comparison and eliminate the noise component. That's the strategy. If that's the case, let's look at this difference amplifier from a slightly different perspective. And before we do that, let's go through some preliminaries. Let's define two new signals. A differential mode, which is simply the difference between voltage source B and voltage source A. We'll call that the differential mode of those two signals. How do they differ? And that might be what's carrying the information, is how do these two signals differ, and what's their commonality? What's their common mode? Well, we can average those two signals and get the common behavior, the common mode of those two signals, V sub A and V sub B. Two new terms, V common mode and V differential mode. If you simply multiply both sides by 2 on that common mode expression, you see that the sum of V sub A and V sub B is going to be 2 of your common mode voltages among those two signals. Let's do some algebra. With these two relationships, this one and that one, I'm now putting this one here and this one there. And I hope you can anticipate that, oh, he's now wanting to add those so that the A voltage disappears. And now I can have a formula for the B voltage in terms of the common mode voltage and the difference mode or differential mode. Doing that, I have 2V sub B is equal to V differential mode plus 2V common mode. Dividing by 2, this is now the expression that I wanted. VB now, that source, just written as differential, some linear combination of the differential mode and the common mode. And really it's the common mode plus 1/2 of the differential mode. That's V sub B. We want to find V sub A in a like manner, which says use those same two formulas, just negate one of those, so that now you're canceling the V sub B component, and that's what the red is trying to indicate. And now we can add those two together to find an expression that only involves V sub A and not V sub B. V sub A now can be written in terms of the common mode voltage and the differential mode. And you can see then that the V sub A and V sub B share the common voltage, and then they have a shift, so to speak, in the differential mode. One goes up and one goes down by 1/2. So let's say we're finished with those preliminaries. That's the end of preliminaries. We now have defined two new concepts, differential mode, VB minus VA, and common mode, the average of those two, VA and VB. Let's now interconnect the sources and see if we can come up with a useful application of the difference amp. Now I've simply tried to build V sub A in terms of the formula. And I'm going to convince myself that I've interconnected this properly by checking my work by writing a KVL. That's what the red dashed is doing. I now have minus V sub Cm plus V sub dm over 2. Then I go through the air gap plus V sub A, and I'm back to where I started. Or, hopefully now this shows me that V sub A is V common mode minus half of the differential mode voltage. And that's what I said it was. That way of interconnecting those two new voltages allow me to create V sub A. And I think you can maybe anticipate by the structure of how I've drawn this, how I'm going to now use this in the differential amplifier setting. But before we get there, let's just do the same strategy for V sub B. And now I'm just going to do a KVL this way. Or I now have minus V sub Cm plus, nope, went into the negative, so I now have minus V sub dm over 2 plus V sub B is equal to 0. Or V sub B is now V common mode plus 1/2 of the differential mode, as I wanted. Now I take the first V sub A structure and the second V sub B structure written in terms of common mode and differential mode and put those into the differential amplifier or the difference amp. Hopefully you can see that I have preserved V sub A at the top and V sub B at the bottom. And I have my differential or my difference amplifier on the right. And I know that you've already committed to memory this expression. There's V sub O. It's the non-inverted piece and the inverted piece. Now, if you want to exercise your algebra and bookkeeping skills, then you need to do the following. Go ahead and substitute this common mode and differential mode parameterization of V sub A and V sub B into our formula for V sub O. And collect terms, and I'm guessing most of you are already finished, and you end up with this. This is in the book, so you don't have to write it down. It's in the notes. You don't, and hopefully you can compare my writing down of this to the books. But this now gives you a parameterized form of the output voltage in terms of the common mode voltage and the differential mode. What was the differential mode voltage? V sub B minus V sub A. What's the common mode? The average. What's in common to V sub A and V sub B? And since we're throwing all these variables around, let's create some new ones. Capital A sub Cm, that's the common mode gain. Capital A sub Dm, differential mode. If we do this relationship again of R sub A being R sub C and R sub D equaling R sub B, wow. Now you might be able to remember that one. What has happened? What happened to the common mode piece? And if we had two signals, V sub B and V sub A, two voltages, and the only thing they had in common was the noise that they were picking up as they were going wherever they were going, on the wire or through the air. They both have noise in common. That's their common mode. Now what have we done after passing it through this difference amplifier? What have we done to the noise? We've annihilated it. We've zeroed it out. We've forced it to zero by throwing V sub A and V sub B, both containing identical noise, but we've remained or preserved this difference mode, and we've amplified it. Now the output is only a function of the difference between V sub B and V sub A, and that's what's holding the information. The common mode was what we, in general, if we had a sensor, or if you now have been hooked up in the hospital, they may be measuring what your heart is doing. Well, you're picking up all sorts of noise on those wires, but they cancel them out. The common mode gets canceled out by putting them through a difference amplifier, or what could be improved upon and made an instrumentation amplifier. Now what they're looking for is what your heart is doing, not what the room environment is doing. They're canceling the room environment noise and interference out, because that's all common in these leads that are connected to you. And what they're preserving is the signal content, the information that your heart might be providing to them. What do you have to remember about today's material? Hopefully when you're in the hospital, the instruments work. Right? And why do they work? Because some engineers designed them to work. They said, what's in common? I can't make out anything with this signal. I can't make out anything with this signal. But boy, if I get rid of their common noise or their common interference, now the signal is very clear what's going on. And that's what is preserved with this difference amplifier implementation. And I know you want more letters to text, so I've given you CMRR, common mode reduction ratio. That's the ratio of these two gains, the differential mode gain and the common mode gain. You want the common mode gain. In reality, it's not going to be zero, but hopefully it's very small. And as it gets small in the denominator, that makes everything big. And typically this might be, the log of this might be taken, and you might see this expressed in dB. But we want the common mode reduction ratio to be large. Questions on that, or was it all just noise? Did you already put it through your own difference amplifier? Huh? I didn't dismiss you. It's still not. I've got plenty of time to go the rest of the way. I wanted to get to this nice magenta scroll. I wanted to redraw some more. How could we redraw? So we'll finish with this. We have a minute. We can redraw this. We had so much fun redrawing the difference amplifier, and the right answer is yes, we did. Yeah, we really enjoyed that. Let's enjoy this one. How can we redraw this? I've already connected the non-inverting piece. How could we draw the next piece? Let's say that here is now our output. But now what I want to do, do you see that I flipped the op amp in terms of I've mirrored it? The plus is now on top, the minus is on the bottom. So you have to kind of pay attention when you're doing the exam. That might be a sneaky way to make you make an error. So that's what you're trying to stay attuned to. But now we want to draw this. So let's say that I have R sub f. Let's just make it vertical. Let's say here's R sub f. And it's actually going back to the inverting terminal. And R sub s is just going to ground. And now, to look at those, on the right and the left, you might go, I thought he said this was a non-inverting amplifier. All I remember seeing is it drawn on the left. Well, now you might see somebody draw it like this on the right, and it's exactly the same. And you need to get comfortable with these morphing strategies of circuits, and you can now rederive this. You could find, and maybe I'll do that after class since I said I would only hold you here for another minute and I've already exceeded that. So we'll pick up somewhere close to that next time.